Good morning. Today we are going to discuss about symmetry adapted linear combination of atomic orbitals or SALC. SALC is one of the most important topic in group theory that is used to create molecular orbitals. And we'll see what is SALC and why is it important. In the formation of molecule, atomic orbitals of appropriate symmetry and comparable energy combine together to form molecular orbitals. We all know that. And the symmetry properties of atomic orbitals provide an easy way in obtaining the shape and symmetry of molecular orbitals. And it is assumed that during the formation of MOs, this is important, all the atomic orbitals of the atoms other than the central atom combine together to form a set of SALCs, that is the symmetry adapted linear combinations. And who all are participating in the formation of SALCs? The atoms other than the central metal or central atom. If we consider H2O, oxygen is taken as a central atom and other atoms are hydrogens. And in this case, the two hydrogens combine together to form SALC. That's important thing. And these SALCs then overlap with AOs. And there is the atomic orbitals here. Actually, the atomic orbitals of the two hydrogens combine together to form a SALC. And the SALC again combine with the central metal atoms AOs to form molecular orbitals. And how will they overlap? They overlap with the AOs of appropriate symmetry. These salcs then overlap with AOs of the central atom of appropriate symmetry to form MOs. The salc refers to symmetry adapted linear combinations which are generated via use of the projection operator technique. We are using projection operator technique to find out how these salts are generated. And these salts are mathematical representation. They are just mathematical representations and therefore bear no physical meaning. And they are commonly used in the generation of molecular orbitals as we have seen. First, the atoms other than the central atoms, their AOs combine together to form SALC, and the SALC indeed, what will they do? They will overlap with the AOs of the central atom, which has the appropriate symmetry and shape and energy, and they will form the MOs. That is what is happening. And when it comes to projection operator, a projection operator is a special type of operator which projects out that part of the function having the symmetry of the species using which the operator is set up, and it is represented by p cap I equal to li by h summation of r chi I of r into r cap. That's what the projection operator looks like. The equations look like where I is the symmetry species of irreducible representation in the character table. H is the order of the group. Li is the dimension of the ith irreducible representation. Chi I of R is the character of each operators, and R cap is the operation that we are doing. And we will, when we are doing the problems, we will have a thorough look at it. And this is the first point, the SALC of C2V point group. And we have C2V point group, C3V point group, C2H point group, and D3H point group to deal with. First of all, during the formation of H2O, the two 1s orbitals represent in H atoms overlap together to form two SALCs. So the SALCs will be overlapping with the ions of the oxygen atom of appropriate symmetry to form MOs that we have already discussed, and the number of salts formed is equal to the number of combining AOs. That is also a very important thing. The number of salts will be equal to the number of combining AOs. The shape and size symmetry of the salts can be formulated in the following way. and we will consider H2O molecule formation of IRs, irreducible representation of C2V point group of H2O molecule. Take 1s atomic orbitals of H atoms. Say SA and SB represents the 1s orbitals of first and second hydrogen atoms. First, we will consider this picture of H2O, and this is termed as H1 and this is termed as H2. And the S1s orbitals are termed as SA for H1 and SB for H2. We have the bonds given sigma 1 and sigma 2. And these are different steps involved in the formation of SALCs. First, we have to generate a reducible representation using atomic orbitals collectively and simultaneously. First, we have to produce a reducible representations. We use chi is equal to 1 for unshifted atom and for shifted atom chi equal to 0. And second, we have to find the IRs, that is the irreducible representation in the reducible representation using which formula? Reduction formula, which we had used earlier, and then write down the projection operator in various symmetry operations of a group. And the fourth one is using the projection operator to find the group of orbitals of desired symmetry. The fifth point is the combine group orbitals of the same symmetry to form molecular orbital wave function, which we are only dealing in the next semesters.